The year was 1935, and America's railroads controlled an empire worth billions. 6,000 steam locomotives thundered across Pennsylvania railroad tracks alone. Coaling towers stretched 12 stories into the sky. An entire civilization had been built around steam power until a small company called Electro-Motive brought it crashing down. But steam's dominance went far deeper than just the locomotives themselves. American railroads had invested billions of dollars in steam-specific infrastructure by 1940. Every major terminal featured elaborate roundhouses where steam locomotives received daily maintenance. Coaling towers, some reaching 12 stories high, dominated rail yards from coast to coast. Water tanks dotted the landscape every 20 to 30 miles, essential for steam locomotives that consumed thousands of gallons per hour. The Baltimore and Ohio Railroad's massive Cumberland facilities could service up to 40 locomotives at once. Teams of hostlers, firemen, and mechanics worked around the clock, cleaning fireboxes, oiling running gear, and preparing locomotives for their next assignments. Steam locomotives required frequent servicing, often every 100 to 150 miles on heavy mainline runs. Railroad executives had every reason to believe this system was permanent. Steam technology had evolved dramatically since the crude locomotives of the 1830s. The Union Pacific's massive big boy locomotives, introduced in 1941, weighed 1.2 million pounds and could generate nearly 6,000 drawbar horsepower under heavy load. These mechanical giants could haul 3,600-ton freight trains over Wyoming's Sherman Hill with little to no assistance. Steam seemed to have reached its technological pinnacle. The Pennsylvania Railroad's T1 duplex locomotives, designed in the early 40s, represented the absolute cutting edge of steam technology. With their distinctive shark-nose styling and advanced valve gear, they were capable of hitting 100 miles per hour on high-speed passenger runs. Railroad magazines proclaimed them the future of high-speed rail transportation. But beneath steam's impressive performance lay fundamental economic problems that railroad accountants were beginning to notice. Steam locomotives spent more time in maintenance facilities than in revenue service. The Pennsylvania Railroad's fleet averaged barely two-thirds available for service at any given time, meaning one-third of their locomotives sat idle for repairs. Maintenance costs consumed substantial portions of total operating expenses, a figure that railroad executives accepted as unavoidable. Labor costs presented another challenge. Operating a steam locomotive required substantial crews, and union agreements mandated specific crew sizes that railroad brotherhoods fiercely protected. On long-distance runs, crews changed every 100 to 150 miles due to federal hours of service regulations. A single freight train from Chicago to Los Angeles might require 8 different crews. The coal industry had grown wealthy supplying America's railroads. In 1940, locomotives burned tens of millions of tons of coal every year, representing a significant share of total U.S. production. Coal dealers maintained supply contracts worth millions of dollars with major railroads. The Norfolk and Western Railway, which hauled coal from West Virginia mines, operated some of the most efficient steam locomotives ever built specifically to showcase coal's superiority as locomotive fuel. Water presented logistical nightmares that railroads had learned to accept. Steam locomotives consumed 50 to 100 gallons per mile, depending on load and terrain. The Santa Fe Railway maintained well over 1,000 water stations across its vast 13,000-mile system. During winter, section crews worked constantly to prevent water tanks from freezing. In desert regions, railroads hauled water hundreds of miles to supply remote stations. Railroad executives viewed these challenges as manageable costs of doing business. Steam locomotive manufacturers like Baldwin, Lima, and American Locomotive Company employed thousands of workers and maintained extensive research programs. The industry had invested too heavily in steam technology to consider alternatives seriously. Then General Motors made a decision that would reshape American transportation forever. In 1930, General Motors acquired the Electro-Motive Corporation, a small company known for building gasoline-electric rail cars for branch lines and short-distance service. Most railroad executives dismissed Electro-Motive as a niche manufacturer with no place in heavy mainline freight. But under General Motors, the company shifted its focus towards something far more ambitious. Diesel-electric locomotives. At the time, diesel engines were widely considered too weak and unreliable for serious railroad work. But GM's leadership saw opportunity where others saw limitations. They committed $20 million to developing diesel-electric locomotive technology. This represented one of the largest corporate research investments of the 30s, rivaling expenditures by major aircraft manufacturers. The technical challenge was immense. Existing diesel engines produced insufficient power for heavy railroad service. Large steam locomotives could generate between 3,000 and 6,000 horsepower at the drawbar. Available diesel engines struggled to reach 1,000 horsepower reliably. Steam locomotive horsepower figures typically refer to drawbar horsepower, power delivered to the rails, while diesel ratings refer to engine horsepower. The comparison wasn't perfectly equal, but diesel's advantage wasn't peak power. It was availability, efficiency, and lower operating cost. Electro-Motive's engineering team, led by Richard Dilworth, developed revolutionary solutions. Instead of building one massive diesel engine, they created modular units that could be coupled together. Each unit contained a diesel engine driving electrical generators, which powered traction motors connected to the wheels. This diesel-electric system eliminated the complex mechanical linkages that limited steam locomotive power transmission. The breakthrough came in the late 30s with GM's revolutionary 567 diesel engine. The 567 produced 1,000 horsepower in a compact modular package that could be combined into multi-unit locomotives. More importantly, the 567 engine demonstrated remarkable reliability during extensive testing. Railroad executives remained skeptical. The Association of American Railroads Mechanical Committee published reports questioning diesel reliability and fuel costs. Steam locomotive manufacturers dismissed diesel as a temporary fad that would disappear once railroads calculated true operating expenses. Electro-Motive needed to prove diesel's superiority conclusively. In 1939, they completed construction of the FT demonstrator, a 4-unit, 5,400 horsepower diesel-electric locomotive designed specifically to challenge steam's dominance in heavy freight service. The FT demonstrator began its epic journey in late November 1939, departing General Motors' LaGrange, Illinois facility for a tour of about 83,000 miles across American railroads. This wasn't a publicity stunt. It was a carefully orchestrated technical demonstration designed to gather hard performance data under real operating conditions. The concept was radical for its time. No locomotive manufacturer had ever sent a single unit across the entire continent to prove its capabilities. Railroad mechanical officers, accustomed to evaluating locomotives on their own territories under controlled conditions, viewed the tour with deep skepticism. Many believed the FT would break down within weeks, proving diesel's unsuitability for heavy railroad service. But Electro-Motive understood that skepticism could only be overcome through undeniable performance. They equipped the FT demonstrator with extensive monitoring equipment to record fuel consumption, maintenance requirements, and operational data. Each participating railroad assigned their most experienced engineers and mechanical officers to conduct the tests, ensuring that results couldn't be dismissed as biased or incomplete. The tour generated unprecedented attention throughout the railroad industry. Trade publications followed the FT's progress closely, reporting on each test and performance milestone. Railroad executives who had never seriously considered diesel power began riding along on test runs, witnessing firsthand the locomotive's capabilities. The visibility was intentional. Electro-Motive knew that changing an entire industry's mindset required more than technical data. It required personal experience. What made the demonstration particularly compelling was its real-world nature. This wasn't a laboratory test with carefully controlled variables. The FT demonstrator hauled actual freight trains over actual railroad routes, facing the same challenges that confronted steam locomotives daily: steep grades, adverse weather, tight schedules, and demanding tonnage requirements. The Santa Fe Railway provided the first major test. The FT demonstrator departed Kansas City with a 3,600-ton freight train bound for Los Angeles. Steam locomotives typically required helper engines to climb Raton Pass, a brutal 3.3% grade through the Rocky Mountains. The FT demonstrator climbed unassisted, maintaining 25 miles an hour where steam locomotives struggled to reach 15. More impressive than raw power was the FT's operational efficiency. The FT completed the Kansas City to Los Angeles run with dramatically fewer servicing stops than steam required, eliminating water stops, ash handling, and coaling delays. This operational advantage translated directly into reduced crew costs and faster freight delivery. Railroad executives began paying attention when they saw the operating statistics. Fuel costs were significantly lower per mile than comparable steam locomotives. Maintenance requirements dropped dramatically. The diesel required inspection every 750 miles instead of every 150 miles for steam. The Pennsylvania Railroad, America's largest railroad, invited the FT demonstrator for extensive testing in early 1940. Pennsylvania's mechanical department subjected the diesel to punishing schedules, hauling 4,000-ton freight trains over the Allegheny Mountains. Steam locomotives typically required double heading, two locomotives coupled together, for these heavy trains. The FT demonstrator proved capable of handling trains that often required double heading with steam power. Pennsylvania's test results shocked railroad management. The FT demonstrator averaged 89% availability compared to roughly two-thirds for their steam fleet. Turnaround time at terminals dropped from 4 hours to 30 minutes. Total operating costs per ton-mile fell substantially compared to steam locomotives. Word spread quickly through railroad executive circles. The Baltimore and Ohio Railroad ordered extensive FT testing on their demanding Cumberland to Grafton route through West Virginia mountains. The Great Northern Railway tested the demonstrator on their transcontinental mainline across Montana's Continental Divide. Every test produced similar results. Diesel locomotives operated longer between servicing, required less maintenance infrastructure, and delivered lower total operating costs. The economic advantages were becoming undeniable, even to steam's most ardent supporters. The Illinois Central Railroad became the first major railroad to place a substantial diesel order, purchasing 36 FT units in 1940. Other railroads quickly followed. The Santa Fe Railway, impressed by the FT's performance on Raton Pass, ordered 320 diesel units, one of the largest locomotive orders in U.S. history at that time. World War II temporarily slowed the diesel revolution. The War Production Board allocated steel and other critical materials to military production, limiting civilian locomotive manufacturing. Steam locomotive production actually increased during wartime as railroads struggled to handle unprecedented traffic volumes with existing equipment. Baldwin Locomotive Works delivered over 3,000 steam locomotives between 1942 and 1945, their highest production in decades. But the war also demonstrated diesel's strategic advantages. Military railroads in Europe and the Pacific relied heavily on diesel power for its reliability and reduced logistical requirements. American railroad executives took note of diesel's performance under extreme conditions. When wartime restrictions ended in 1945, pent-up demand for diesel locomotives exploded. Railroads that had deferred modernization during the war placed massive orders. The New York Central Railroad, Pennsylvania's primary competitor, kicked off a massive post-war dieselization program, ordering hundreds of new units starting in 1946. Steam locomotive manufacturers fought back desperately. Baldwin Locomotive Works introduced the superpower steam locomotive concept, featuring larger fireboxes and improved efficiency. The Norfolk and Western Railway developed the J-class steam locomotives, which achieved thermal efficiency rates approaching diesel performance. But Baldwin's efforts to compete in the diesel market proved disastrous. Their diesel locomotives suffered from reliability problems and poor design. Railroad customers complained about frequent breakdowns and excessive maintenance requirements. By the early 50s, Baldwin's market share had collapsed to a small fraction of what it had been during the steam era. The economic mathematics were inexorable. Steam locomotives required extensive support infrastructure that diesel eliminated entirely. Coaling facilities, water stations, and roundhouses represented massive fixed costs that railroads could eliminate by converting to diesel power. Diesel locomotives transformed railroad terminals completely. Where steam locomotives required elaborate servicing facilities, Diesel units needed only fuel and basic maintenance. Terminals that once sprawled across hundreds of acres to accommodate coaling towers, ash pits, and water facilities could be consolidated into compact diesel servicing areas. The Santa Fe Railway's Barstow, California terminal exemplified this transformation. Steam-era infrastructure was consolidated into far more compact diesel servicing facilities. The operational changes were equally dramatic. Steam locomotives typically required 4 hours of terminal time between runs for coaling, watering, ash removal, and mechanical inspection. Diesel locomotives could be refueled and inspected in 30 minutes. This faster turnaround meant railroads could operate the same number of trains with fewer locomotives, dramatically improving asset utilization and reducing capital requirements. Labor unions initially resisted dieselization, recognizing the threat to employment. The Brotherhood of Locomotive Firemen fought particularly hard to maintain fireman positions on diesel locomotives. For firemen, the job represented more than employment. It was professional identity and the traditional path to promotion to engineer. Union leaders understood that eliminating fireman positions would fundamentally alter railroad career structures and reduce union membership. Railroad management gradually negotiated crew reductions through complex labor agreements. Many railroads agreed to maintain diesel fireman positions for years, even though these workers performed minimal actual duties compared to steam firemen who shoveled coal and maintained steam pressure. The Pennsylvania Railroad's labor agreements required diesel firemen until 1963, nearly 2 decades after dieselization began. These negotiations reflected the social reality that technological change couldn't be imposed overnight without considering human consequences. The transition occurred slowly, with full crew reductions not achieved until the 1960s in many cases. Railroads used attrition, early retirement programs, and retraining to manage workforce reductions. The process required patience and substantial financial investment in severance packages and pension enhancements, but it allowed railroads to achieve long-term labor cost reductions while maintaining labor peace. The Pennsylvania Railroad's conversion illustrated the dramatic changes occurring across American railroads. In 1940, Pennsylvania operated over 6,000 steam locomotives. By 1945, they had ordered 574 diesel units and begun retiring steam locomotives en masse. Their massive Altoona shops, which had built steam locomotives since 1866, converted to diesel maintenance and repair. Pennsylvania's locomotive workforce declined substantially during the diesel transition. Skilled craftsmen who had spent decades maintaining steam locomotives found their expertise obsolete. Many workers retired early or transferred to other railroad departments. The social impact extended far beyond railroad employment, affecting entire communities built around steam locomotive maintenance facilities. Steam locomotive production collapsed with stunning speed. American Locomotive Company delivered 1,544 steam locomotives in 1944, but only 274 in 1948. Baldwin Locomotive Works, America's largest steam locomotive manufacturer, delivered their final steam locomotive in 1949. Unable to compete effectively in the diesel market, Baldwin merged with Lima Hamilton in 1950 and exited the locomotive business entirely by 1956. The Norfolk and Western Railway and Chesapeake and Ohio Railway held out longest, continuing steam operations into the late 50s. Both railroads hauled coal and viewed steam locomotives as advertisements for their primary commodity. The Norfolk and Western's mechanical department developed increasingly efficient steam designs, including the legendary Class A2664 locomotives that could match diesel fuel efficiency on certain routes. But even these steam strongholds eventually succumbed to diesel's operational advantages. By 1960, even the legendary Norfolk and Western's steam giants had fallen silent. The Chesapeake and Ohio phased out regular steam operations by the mid-50s. With their conversion, mainline steam operations effectively ended in the United States. Railroad infrastructure transformed completely during the 40s and 50s. Coaling towers were demolished or abandoned across the country. Water tanks that had served railroads for decades disappeared from the landscape. Massive roundhouses were converted to diesel maintenance facilities or torn down entirely. The Pennsylvania Railroad's roundhouse in Altoona, which once serviced 200 steam locomotives daily, was demolished in 1963. The Baltimore and Ohio's Cumberland Roundhouse, an architectural landmark, was abandoned in the 50s and eventually torn down years later. Across America, the physical infrastructure of steam railroading vanished. Scrapyards filled with retired steam locomotives during the early 1950s. Thousands of locomotives that had served faithfully for decades were cut up for scrap metal. The Pennsylvania Railroad alone scrapped thousands of steam locomotives between 1945 and 1960. Many historically significant locomotives were lost forever during this period. Coal mining communities that had supplied locomotive fuel faced devastating economic collapse. The United Mine Workers Union lost hundreds of thousands of members between 1945 and 1960, largely due to reduced railroad coal consumption. Entire towns in West Virginia, Pennsylvania, and Kentucky withered as demand for locomotive coal disappeared. Diesel locomotive technology continued advancing rapidly. Electro-Motive introduced increasingly powerful models: the F7 in 1949, the GP7 in 1950, and the SD7 in 1952. These locomotives offered improved reliability, reduced maintenance requirements, and lower operating costs than their predecessors. By the end of the 50s, diesel locomotives comprised roughly 95% of American railroad motive power. Steam's century-long dominance had ended in barely 20 years,